Hello, this is chapter 17, lecture 27. This is 17.2. We'll be talking about momentum methods. So we finished 17.1 talking about energy. And so this is a good segue because now we'll look at what happens when we apply or try to solve problems using momentum methods on a rigid body. And as you'll find is that there's not often you don't have just both methods in a problem. There's a lot of times that they'll commingle. Part of it'll be using momentum, part of it'll be using energy. But to get started, let's just go through the theory of it, which isn't much. Not if you've looked at the section, you see there's maybe 3 pages. There's not a lot to write down, but just to get the main idea. So and actually before I show this, I like this point here. It says method of impulse and momentum is well suited to the solution of problems involving time and velocity. So remember we talked about how do you know what method to incorporate when you're solving a problem, because on the final it won't say use energy, use F equals ma. So this is something you'll probably want to jot down to yourself if you already haven't on your sheet for the test. But the fact that if you do have time and velocity, then chances are impulse momentum is going to be the best way to solve it in terms. All right. And so obviously impact, any type of impact is going to be impulse and momentum. And so that's kind of a giveaway. But just like before, we've seen this before where you have a system now and you have the momentum of the system that has to be conserved. So any impulse that's applied, which is a force over time, then you get a resulting final momentum. And so nothing's changed. You essentially have your m1 v1 plus the integral of f dt equals m2 v2. So that's the same. The addition, though, is this idea. So momentum of the particles of a system may be reduced to a vector attached to the mass center. Okay, so that makes sense. You can take all of the momentum for all the particles or everything in the system, and just like you could attach a force vector at the center of gravity, you can attach a momentum vector at the center of gravity. And so now the right picture here, you recall in the earlier, it would say F equals ma, and the difference is now we have L equals mv, or the momentum of the center of gravity. And then that's also going to be coupled with the angular momentum of the center of gravity around the center of gravity. So I omega. And so we can also write this as simply the linear momentum equals, the angular momentum equals I omega. So we know that the change in momentum we learned earlier about, and now we're just going to take this relationship and use it. Now, if you have multiple systems, then you may use the R cross V at delta M, but generally the problems we are not going to give you multiple particles with it, but it just shows that it is possible to sum all those vectors together to get the end result. And so we end up with, if we do like before, we end up with this kind of system here where we write it as m1 v1 plus your I omega, gives you your adding your force over time, and then gives you your mv2, so your final momentum, and then your final angular momentum. So previously when we did particles, we'd start with momentum, we'd do a force over time, we'd end up with our final momentum, but it was always linear momentum, or it was only angular momentum, but we haven't really combined the two, and that's what this really does. You can think of the mv2 arrow as the linear portion and the I omega as the rotational portion. Oops. All right. Oh, actually, before we go through that, there's one thing that I want to mention. And that's the fact that you also have to deal with your angular momentum change. So what does that mean? Let me stop share. So we know that we can write our equation mv1 plus the integral of f dt equals mv2. So essentially, if we think of it as this is the initial plus our impulse, and that gives us our final. So that's nothing new. But the other thing that I wanted to mention was that in addition to this, we also have the I omega. So we may have I bar omega, right? And that's angular momentum, right? Rotation times a moment of inertia. And so what are we going to add to that to increase it or decrease it if we take away? Well, it's going to be then the integral of the moment dt. Okay. So that's not, it's mentioned in that chapter, but I don't think it's called out as well as it should be. So just like this is, that has this, then here you're just going to add your moment, a sad looking integral, but, and that's going to equal your final I, we'll call it omega 1 and I omega 2, since I doesn't change. So I wanted to point that out because that's going to be important in some of the problem solving we do. All right. So let's look at a theoretical question. And so what we have there is a slender bar, and we have slender bar A is rigidly connected to a massless rod BC in case 1, and 2 massless cords in case 2. So the bar BC has no mass, but and so really all you have is A. So the masses are identical in both cases. So the question then is, if you shoot a bullet into A, and then the momentum is transferred, as we saw in an earlier example, then we predict that and there's no friction, we predict that that whole mechanism is going to pivot up as shown with the dotted lines. So the question then is, thinking about it, how will the speeds of the center of gravity of A immediately after impact compare for the two cases? So what's going to be the V naught of the center of gravity? Are they both going to be the same since they're the same mass, or are they going to be different? So in this case, you want to think about what's going on here? So, well, so if you guessed case 2, then you were correct. And so, but why? And so if you want to think about for a second and then press play, you can, but it comes down to case 1 has both linear and angular momentum. So if you think about this block down here at A, it's going to have to rotate, even though it's connected to this massless thing. This block or rectangle with A in it does actually have an omega attached to it, but it also has a translation. So because you have both those momentums you have to conserve, that means you're going to have less end velocity, because some of that velocity is eaten up in the momentum. Whereas in case 2, you just have essentially a translation. So that's the idea with that one. All right. Oh, now we did talk about impulse momentum diagrams, and you may remember earlier on I showed them to you. We didn't do a lot of them, but for the final, please make sure that you draw good diagrams for everything, because as I said, as other instructors can be grading your work, and you don't want to lose points for silly things. So this one, that's not really a calculation, it's just we're going to draw what does the impulse momentum diagram look like. So you have this, you have this wheel that has mass, obviously it's not massless, and then you have the radius of gyration is given, you're given some values. So this could be a problem, I mean, an exercise to solve, but we're just going to look at it as, what is the free body or what does the impulse momentum diagram look like? So here, and this is something I haven't been as diligent about as I should be, but this here should go on every problem you do. So write that down. You should put YX moment on everything, except the conceptual problems. But the 4 problems that we do on the final, 4 or 5 problems that are full calculations, please write that on there. Okay. So if we look at our impulse momentum, very simple. Here we have mVB, right? And then we have our I omega. So that's the difference. Before with particles, we just had M1V1. And then we had the middle piece, which was our impulse. So notice all I've done here, like before, is I've added, there's the weight times time, the reaction A in the X times time, the reaction in the Y times time, and then the weight of B times time. So that's really all you're doing is your external impulse. You're just taking all the reactions here that would normally be your forces that you would do in a free body, and you're just adding a time component to them. That's it. So just make sure you do that in an impulse momentum problem. And then you get your final, which of course is just your I omega 2. And then you're going to have, this would be your linear momentum. This would be your angular momentum. So you've accounted for it. Okay. So again, system momentum plus external impulse equals final system momentum. Or you can write it like this, or depending on the problem, it will be the I omega plus the integral of the moment over time equals I omega. We'll say this is omega initial, omega final. Okay, that's all there is to it. Yes, that's Frito. See if he says hello. That's Frito. So he's here making sure that I do the job I'm supposed to. So if you hear any cries of pain, it's because I messed up. All right, back you go. All right. Okay, so let's go on to the next one. All right, so then here, this is not a problem. This is just another impulse momentum diagram. And so here's what it's going to look like. Maybe I shouldn't have taken your thunder away. So if you want, pause and try to draw it if you feel the need as practice, and that couldn't hurt. So pause here, and now start up again. All right. So if you did start up again, then here it is. So you have A. So the only thing is connected because the rope got taut. Before it was just in free fall. So you knew you had the momentum of the free fall, mv naught, initially before it was taut. So there's nothing at A. Then when it hit A, you had a integral. It's a horrible integral. The integral of A dt. So you have just, again, like I said, you have the reaction, which you know that is in that direction because of the rope over time. And that's all there is. Although I would have put this thing, I guess they're assuming that it has no mass. I mean, they put mass times velocity here, but it seems like you might want to put the weight times time. So I would have added that in this case. And then you get your final, which is I omega, because now it does have an I omega that's going to spin. And then you have your MV, and then the ML over 2 omega, which is, that's just your torque, your I alpha. Okay, so just another example of these. I think this one's okay, but I like the previous one we did here. I think that's gonna be more relevant to what you're gonna see. And just do the best you can on these. If you leave out something, it's not the end of the world, but just I would look at a few examples in the book to get a sense of what they look like, and then just add whatever is necessary to make the diagram complete. Okay, let's do a simple example. Now this one is doesn't take much. It's just a simple setup, but it's just meant to show you what the moment over time is. So we have this cube and we have a cylinder. So effectively what you're going to do is you're going to find the moment of inertia of the entire piece. And then you're given a couple, M is 20 Newton meters. And you're going to want to apply, you want to essentially see how much time does it take to increase it from 1,000 to 2,000 RPM. So this is really just a plug-in problem with the very simple equation I showed you. But just to get familiar with the terms, let's go ahead and do that. So here's our diagram. We have the cube, we have moment twisting it. And so we know L is 300. The radius of this little shaft here is 100. So we know that I of the cube is equal to 1/12. And what is the mass? It's, oh yeah, the mass was 75 kilograms for this. And then the shaft was 70 kilograms. All right, so we have 112, 75, and then that's going to be 0.3 squared plus 0.3 squared. All right, so that gives us a value of 1.125 kilogram meter squared. Then we do I of the cylinder. And that's going to equal just 1/2. Oh, remember, not ink, I mean lead. Grab another pencil. So that's going to be 1/2 70, and then times r squared, which was 0.1 squared. So for that, we get 0.35 kilogram meter squared. So our total I bar is 1.475 kilogram meter squared. And of course, we can add them because we're assuming rotation is right down this line if we were to draw it. Okay. So this is really, we start off with our I omega naught, and then we add it, what, an integral of m dt, and then that gives us our I omega final. So there's not a lot to this problem, because really, if we set it up as I omega naught plus mt equals I omega final, and that's I bar, then really time is just equal to I times omega final minus omega initial all over the moment. Okay, that's big M. So 1000 RPM, we know we can convert that with 2 pi. So we know that omega final and omega naught is going to be 200. I'm sorry, it's going to be 200 pi over 3, and this is going to be 100 pi over 3. There we go. So 100 pi over 3, yeah, radians per second from RPMs, the radians per second. So all we do is plug this in, then we just have what our value is, which is the time is 1.475 kilogram meters squared, and then that's going to be multiplied by 200 pi minus 100 pi all over 3 radians per second. And then on the bottom, we have the moment, which is in Newton meters. And we're given that that has a value of, what did that value be? I guess I should have wrote that down. 20 Newton meters. So we know that M equals 20 Newton meters. That was in the problem. So 20 kilogram meter per second squared. So I don't usually go through unit analysis, but here we have. So we can see that times meter, right? So Newton meter. So the meters squared cancel, kilograms cancel. The seconds cancels with that. That comes up at the top. So yes, we end up with T equals about 7.72 seconds. All right. Easy problem, just to show you this. And that's all we're going to do. We're not going to have any integrals. I'm not going to give you any functions that you have to integrate. It's just basically going to be torque over time, just like force over distance, or force over time, sorry. All right, so here's a slightly different one. It looks simple, and it isn't really difficult. It's just there's The important thing in this, especially if this were on the exam, would be your ability to draw the correct diagram. You want to make sure for each one, because the calculation itself isn't hard. So let's go ahead and set up the initial calculation. So looking at this before I actually draw it, we see we have a 3-pound carriage. So I would pause this point and write this down. So a 3-pound carriage, 2-pound discs, two 2-pound discs, so A and B both weigh 2 pounds. And then given the radius is 3 inches, and then we know it's at rest, so we want to determine the velocity of the carriage 0.5 seconds after the 0.2 pound force P has applied. So these aren't wheels. You can kind of think of it in a sense, and it doesn't really matter. So, but what's going to happen as soon as it starts to move, C is going to move and A and B are going to roll and move. So they're going to translate and rotate. C will just translate. All right. And I guess if you think about eventually, the C would roll off of A and B because it probably wouldn't keep up with it because we're assuming no slipping. But we don't care again. It's only that instant, that 0.5 seconds afterwards. So let's go ahead and set it up. So here's my diagram to start with. So what do I have? What I've done is I've drawn VC. So there's the velocity of C. And then this is a wheel. We can just do wheel A or B. We'll do A because A and B are going to be identical. So, but we start with wheel A and we see that VC, that's the velocity of C at the top of the wheel. The velocity of A is in the middle. And then this is going to be what we call our instant center, right? Anytime on the ground, that's going to have a velocity of 0. So instant center velocity equals 0, just a reminder. And then, of course, omega A. All right. So we can then write that the velocity of C is going to equal to omega A times 2 times the radius, because it's 2 times the radius. So then that leads us to know that, and we know that omega A equals omega B. They're the same. There's no slipping, and of course, that gives us VA, which is that's going to be, of course, 1/2 of VC based on this, right? So VA is half of VC. So it's an important relationship, especially if for whatever reason on the chapter 15 problems, the plane motion. Remember that if you have a circle, you want to remember that this point here is 0, and this is going to be half of that. So just something that I would note. So once we have that, let's go ahead, and this is for my impulse momentum. So in this case, there's going to the left, we have MVC initial, which is 0. All right. And then if we look at this, we have the arrow and we have P times T, right? And then the rest of the stuff, we have we're going to write the friction. So we'll have, because there's some friction rolling, so going that way. So we'll call that the friction of A times time. And then we have the friction of B times time. All right. And then, of course, normal force of A times time, normal force of B times time. And of course, that does no work because it's perpendicular direction of travel. We still want to include it. And then lastly, we have this, which is just mass times VC final. All right. Okay. So now we'll do our circles, or actually, well, we can develop an equation, right? From this, we can say 0 plus PT minus F, and we could call it 1 or 2 or A or B, it doesn't matter. So we'll just say F, maybe I'll change that to 1 and that to 2. So F1T minus F2T equals m of c bc. So we'll call that our first equation right there, right? And that's just the impulse momentum, right? There's zero initial. This is all the momentum that's our impulse that's acting in the direction of travel. And then the final. And that's all that is. So now let's look at what the circle is, or what, I'm sorry, what the disc are. Discs. So I did change something quickly. I renamed these F1, F2, N1, N2. And looking at my notes, I realized the reason I did that was because when we go to draw the diagram for the wheel A, we're going to keep that F1, N1. That's the normal force of the rectangle onto the wheel. And then we're going to name the normal force and friction force of the wheel at the bottom. So it makes sense. The friction force is opposite up here and here. And then we know that when you're traveling, the friction wants to push the ground backward, and effectively the friction is going to push this forward. So we have it's not propulsion in this case. So whether it's sliding or not, it's not, because we know there's omega. And so, but what we end up with is this relationship where everything balances out in terms of the forces. And then if we take the moment, the sum of the moments about the instant center, right, which we know to be what? That's this point here, right? That's our instant center. So what do we have then? Well, we have F1 times t times 2 times the radius, right? And then, so that's our moment, okay? And then, as we know, that's going to be our left side of the equation because we have no initial. So this is 0. So really what we're writing is we're writing 0 plus our mt, and that's going to equal r I omega, okay, plus mv. So we're putting that in over here. So my moment about IC, that's the left side of the equation. So I'm going to write that in there. And so I have the force times time, that's it. And then that is going to equal the other side. So this is just my moment about IC. Then that's going to equal what I have going on here, which I know is 1/2 mr squared, right? Because that is the moment of inertia of this. And remember that up here, we know that VC equals omega A over 2R. So we can also write that omega A equals VC over 2R. So what we're going to do is we're going to substitute in, instead of having omega down here, we're going to put in the VC over 2R. So mr squared VC over 2R squared. Okay, just that substitution. And then what else do we have? We have then plus MA, mass of A, and then the velocity of C is what? 1/2 velocity of A. So instead of putting velocity of A in here, we're going to put 1/2 velocity of C in here. And then that's all times the radius. Okay. So now what we have is our initial equation. And so we can go ahead and simplify that. Now, one of the things I didn't explain, going through this, is you're probably wondering, why did I multiply this by r? That has to do with the fact that if you remember earlier when we talked about if we had object moving and we took the moment about a point other than center of gravity. Remember how we had F equal the sum of the moments, and then at the other side, we would have I omega. So we had, just real quick, here we had sum of the moments equals to I omega plus M AD perpendicular. So remember that? Well, that happens here too. So in the previous examples I showed you, we were always rotating about the center of gravity. But in this case, on this problem, what we've done is we have moved our point to the instant center, which is not the center of gravity. So effectively, we want to know the moment of momentum is what we're doing. So we're taking the momentum times this radius, and that's really our angular momentum, and that's what this becomes. So it's taking it still has the initial impulse, and then you have your force over time, or your moment over time, really, and that's what this is, moment over time. Notice how it's F times time times the radius to give us a moment. And so to keep things consistent, we have, of course, I omega, which we substituted, plus our moment times the distance. So it's analogous to the MAD perpendicular term we did before. And just remember, anytime you're not at the center, you have to do that. Okay, so hopefully that's clear. I realized I was sitting here that I skipped over that piece, and someone probably would have asked in class. So I've had kind of to anticipate what you guys might want to say. Okay, so now we have that, we can go ahead and simplify this thing. And so we end up with 2 F1 T, because we can divide out the R, right? We can divide out at least one of the R's out of everything. And we know that we're going to divide out, we have this R here, so that's going to get rid of that R there, and then there'll still be one R there, so then we'll divide out of the R, so the R disappears. So then that's going to equal what? 1/2 M R, not R squared, M, oh wait, I'm sorry. That's going to equal, yeah, so then we have a 2. So yes, so it's going to be 1/4, because so it's going to be 1/4 M, and then it'll just be VC. Should be VC, yeah. But that term is squared, so that should be, yes, of course. This square doesn't belong here. I apologize for that. I was thinking I omega squared from energy, but no, that's not there. So yeah, so 1/4 M VC, and then plus 1/2 MVC. Now our masses, it's MA, okay? I didn't put MA, but we know it's the mass of A, so it gives us that. So now we can simplify some more with this. So now we can simplify this further. If we divide both sides by 2 and add this, well, what does this really equal? Quarter plus a half is 3/4 MV of C, right? So F2F, sorry, T. And so our final equation then is, if we divide 3/4 by 2, we get 3/8. So we get F delta T, or change in time, T, whatever, equals 3/8 of massive A VC. And so we can call that F1, and then we can say F2 delta T equals 3/8 massive B VC, since it would have been identical. All right. Well, now that we have relationships for this, we can go back to this equation here. We have a relationship for this and for this. So now, and then we should be able to solve, hopefully. So what do we have? We have 0 plus, and Right, original equation up there. So 0 plus PT. So that goes away. And then that's going to be minus 3/8 MA BC minus 3/8 MB BC equals MC BC. So simplifying that, we get VC equals P times time divided by 0.75 MA plus MC. All right. So all we did here is we know that MA equals MB. So 3/8, 2 times 3/8 is 6/8, which is a quarter, and then we added MC to it, right? Because that's separate, and then we factored out VC. So if we plug in our numbers, we get VC equals 0.2. That's our 0.2 pound, right? Times the time, which is 0.5 seconds. We divide that by 0.75. And then what's our mass? It's 2.0. So 0.75, remember, we don't just put in 2.0, we got to put in 2.0 divided by 32.2 mass. And then plus 3.0 over 32.2. Okay. And that's it. So we solve and we get VC equals 0.716 feet per second. So that's a good problem because it covers the impulse momentum diagram. It covers the free body. You have to take into account normal force doesn't matter, but note that I think the trick here, not the trick, but the thing that might not have been intuitive initially was the fact that we took the moment about the instant center, and so we had to add this R up here to our momentum. So angular momentum plus R I omega. All right. All right. So let's look at this example. And what this example represents is here we're going to be, well, we will initially rotate about our center, but notice again, we have the 10 kilograms sitting out here. So we have double pulleys. We have a moment of inertia of 0.25. Inner radius is 0.1 meter, outer is 0.15. And so we want to know, essentially, it starts at rest. You release the 10 kilogram block. And what's the velocity of the cylinder 3 seconds after the system is released from rest? And then tension in the cord connecting the pulleys. All right. So again, we're going to use, as you guessed it, impulse momentum. Take a second to look at this, maybe sketch it, pause. So there's my drawing. So we notice that this is B. Sorry if the light doesn't show up really well. So there we go. So we have omega A, omega B. This cord here is connected to the inner pulley here at the radius of 0.1. And then D out here is at the outer radius, which is 0.15. So I've put point D there because however fast point D moves is related to how fast C moves. And so we can write this here as velocity of D is equal to R times omega B, right? So the velocity of D is going to be the same speed as omega B times 0.1, which we know is that. We know omega A is going to equal 10 VC. Now, how do we get that? Well, we know that essentially it's R times, I'm sorry, it's divided. So if we take, basically we substitute, we take omega b equals 15 VC, and we know this relationship, velocity of d, is like we learned in the problem we did in class with the disk and the inclined plane. We know that the ratio of the radii gives us these respective velocities. So if we know that the velocity of d is 1.5 velocity of c, then using these respective radii, we can get this. So you could see that if you divide by 0.1, you're going to get 10. That's where that comes from. So we need those to reconcile what's going to happen. So again, once we have that, then we want to look at our impulse momentum diagrams. So we'll start with pulley B, or the disk B. So we know its initial omega is 0. So there's 0 for that. We know that its impulse is going to be the tension at D times time. And then, of course, that's going to give a moment. So we know that that's going to have to be multiplied by R, right? And then the final is just going to be the I omega. And because we're going about the center of gravity, we don't have that MVR term afterwards, right? So that doesn't exist like it did in the other problem. So if we write our equation for this, then we essentially have tension D times time times R, and that's going to equal my I omega B final. Do that, say final. And so there's that. So if we go ahead and plug in a few things, we can simplify this, because we know that this is going to be T tension D times time times 0.1, and that's going to equal R 0.25, right? Because we were given the I for this value. And then we know that omega B, as I found up here, is 15 VC. So I'm just going to write times 15 VC. And you'll see a lot of this conversion between velocity and omega. So if you can wrap your head around this quickly, that'll help you save time during these problems. So just get used to this relationship. So simplify that, we get the tension D times time equals 37.5 VC. All right. So that's one equation we'll put on the back burner for now. Then do the same thing with A. So this was pulley B. Now we have pulley A. So pulley A again, we have the mass times velocity of C initial, and then I omega. We have the tension pulling back over time, and then we have the I omega final and this final. So again, we're starting at rest, so there really isn't anything in it. But so if we write the equation for this, we know it's going to be the weight of C times time times the radius, right? So in this one, because we have this block sitting over here, that's going to create a moment, isn't it? And so we have to account for that, just like angular momentum. So it can be here or it can be there, but it's going to be the weight times R, which is a moment, times time. So we're going to have that to start with. And then we're going to subtract that from tension D times time times the radius. Okay, so this will be R1, this will be R naught. And so just so we're clear, R1 was 0.1 and R outer we could say inner outer, it was 0.15. All right. So we see that here, tension. So this is just the moments, right? This is the MT, right? Because we have 0 plus MT equals I omega. So that's what this is, these two relationships. All right, so paper, yeah, we got 20. So come up here. And so then on the other side, we have, this is going to equal I bar omega A plus the MC VC times R. Okay. So we have to, again, we have the moment, and then that's going to equal the I MAD, only this is, so that's the I omega, and this is your angular momentum. Okay, so they're all related, but not exactly. So now that we have that, let's go ahead and put in our numbers and see what we get. So taking this, what we get, let's start over here. So we have a 10 kilogram mass. So we have 10 kilograms times 9.8 times the time, which we're given as 3 seconds, and then times the radius, 0.10. All right. Minus, and then the tension D, which we don't know, times 3 seconds, times the radius, 0.15. Okay. That's going to equal 0.25. So that's our kilogram meter squared. And then times omega. But we know omega is also 10 VC, so I'm going to put 10 VC in there for omega. Omega A equals 10 VC. And then plus, what do we have? 10 VC times, yeah, we have yeah, then 10 MVC times the 0.1. Okay, I made a slight correction while I paused. So what I did is I took this equation, that hasn't changed, and let's go through it again real quick. So 10 kilograms times 9.8 gives me my weight, my time, 3 seconds, my radius, inner, 0.1, minus TDT. I left it as TDT. I could have put the 3 in there, but I'll explain that in a second, times the outer. That equals I, which is 0.25, times omega A, which we know is the same as 10 VC, plus the mass, 10 kilograms, times VC times 0.1. So if we simplify that, we get 29.4 minus 0.15 TD times T equals 3.5 VC. Now, why did I do that? Because you may recall that earlier I had this equation. TDT T equals 37.5. So we developed that from pulley B. So just like all our problems, we usually have a multiple unknowns, so we make multiple equations, and then we're able to substitute. So we're going to take the TD times time and substitute 37.5 in that. So we'll go ahead and plug in 37.5. And so if we put 37.5 VC in for this, then we end up with TD equals 37.5 times 3.23 over 3, and that gives me the tension D equal to 40.4 newtons. Okay, and that's all I did. So now it might seem kind of weird that I did that because from this step up here, by plugging in this VC, because ultimately we wanted this, right? So what I did is I plugged this in here, and then notice that the only unknown now is VC, 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 VC. So if I solve this, I get VC. Actually, let me just write it down here. Sorry about that. So it's going to be 29.4 minus 0.15 times 37.5 VC, all equals 3.5 VC. So my VC ends up being 3.23 meters per second. But remember, I know that TD times time equals 37.5 VC. And that's where this came from, right? So I take 37.5 times 3.23, divide it by 3, and voila, I get TD. And that's this. So the units up here, though, were in, when they came out, just for clarity, were in, as I recall, millimeters. Yeah, they stayed in, no, they were in meters. Okay, so yeah, Newton meter seconds. Yeah, 0 Newton meter seconds up here in this equation. All right. Okay, so hopefully that helps. I think that's a good place to stop. So that's what I would have gone over tomorrow. I'm doing this on Thursday night. And I will see you guys in office hours if you have any questions. Otherwise, Monday, we'll probably do one more example of impulse momentum, depending on what questions you have. And then we may be able to start reviewing soon. Okay? Sooner than we thought. Thanks, you guys. Have a good night. Well, actually, it'll be a good day by the time you see this, but I'll see you soon. Bye bye.